Yeah, so I guess probably now it's the time to start. So I'm just going to make a brief introduction to our speakers. Hyung Jin is associate professor at School of Computer Science, University of Birmingham. He was a Turing Fellow and at Allen Turing Institute. He did his PhD at National University. He did his bachelor and PhD in National University. I believe that's the best university in Korea. I think this. And then he did his postdoc at Imperial College London with Professor Yanis Demiris, which is actually a professor that I know very much as well, because I'm doing assistive robotics, and Yanis is one of the world-renowned scientists in assistive robotics. So I think that's actually where our connection started, and we met in conferences and in all kinds of occasions a lot of times. So I thought it was really good to invite him over, because basically Hyung Jin's research is actually at the intersection of machine learning, computer vision, and robotics. This is a really rare case that actually you can combine this together, and he did a lot of research on actually human intention, human pose estimation, which is really important. I think for this institute particularly, because we're investigating to safe autonomy, where actually human is part of the safe autonomy. We have to basically interpret and monitor the human intention correctly. Then that's basically computer vision is one of the primary ways to do this stuff. So I believe that his talk will be very interesting today. So without further ado, I give the floor to you.
Thank you very much. Thank you very much, Jihong. And thank you very much, everyone, for having me today. So actually, it's my third time visiting New York this year. So I attended the opening ceremony of the institute. I was so impressed about all the possibilities you guys have. And I think it's very exciting, maybe we can have more further collaboration in the future. So I want to introduce my work first, and then maybe we can have further chat afterwards, right? And because my work is mainly about the computer vision research. I'm not sure how much you are familiar with computer vision, but I'm not going to go very detailed of the algorithm today, because I want to introduce the overview of my research. So I put a lot of videos, so I can this. So hope you guys relax a little bit after lunch, and enjoy the time. Okay, so I'm Hyung Jin from University of Birmingham. So in Birmingham, I'm from School of Computer Science, and we have intelligent robotics laboratory. I mean, compared to your facilities, nothing really. It's very small compared to the robots and the system you have. But we have some couple of robots and the eye trackers and the motion capture system. So I'm interested in the human robot interaction, vision-based human robot interaction really. So this is my group. So we have very excellent research together. We have two postdocs working very actively and 7 PhDs working together. But not only that, we have many global partners, including the Seoul, the Korean partners and universities, but also with Google and NVIDIA very close. And this is my research. So I'm working on the machine learning in general. I'm not sure whether you guys can see clearly. It's okay. Okay. The machine learning. So most of cases now is deep learning based approaches. Now I'm going to tackle the computer vision tasks, and then try to merge those algorithms and the approaches together to enhance the human-robot interactions. So there are 4 fundamental questions I have in my group. So this is not a very short-term one. This is going to be very long-term. I'm not sure it's going to be continued till my academic career ends. But these are I think, very important questions that I have to try to find the answers. So the first thing is how best to recognize humans by appearance information like postures or attributes, etc., etc. This is typical computer vision task, right? And then, based on this explicit information, how can you estimate the hidden information of humans? So most of cases, I'm focusing on the humans, which is like, in this case, like, the characteristics or mood or attentions, intentions, or biomechanics of the humans. And then, because I believe that sooner or later, humans will be very closely collaborating with robots, which is AI system. And then this AI system, human components should be embedded well, right? That's what I want to do. So I want to find a representation or embedding method that of the human component into the AI system. It can be the mesh model, like typical computer approaches, or it can be a text form, or it can be any kind of form. So that's like open question. And then based on this human embedded information, the robot, like AI system, has to reason all the processes, right, properly. That's my four fundamental questions to tackle. So for this task, we are very much heavily working on the fundamental deep learning in the problems, which includes graph neural network, or domain adaptations, or transfer learning, active learning. So we have some publications here, but mainly we are focusing on the four components of the human. I would say five, sorry. 5 components of the humans. So those are including eye gaze estimation, and hand pose estimation, and full body pose estimation, and also the object which is interacting with human, and also the environment surrounding the humans. So we try to understand or represent well, or reconstruct these all 5 components much more accurate way, efficient way, proper way. That's what we've been working on. We have many publications so far. But today, I'm going to mainly talk about these 3. I introduced our 3 recent works. Okay, so the human pose, hand pose, and eye gaze. So, to tackle these issues, we are taking some key research elements. And the combination of this research, and by combining and merging this research key element, we try to find some kind of rooms that we can improve, or some challenges we can tackle, or new approaches we can read. And these are the 5 keywords we mainly focused on last 2 years, my group. So those are including global local information, and the attention, 3D rendering, and spatial temporal, and the generation. So today, this work, now I'm going to show how these components are combined to tackle or to propose design a new algorithm. And that's my answers to. So the first thing is human body pose. So among these 5 components, I first interested in like a global local information combination, and also spatial temporal and attention component. And by doing that, we could make a new algorithm about the human body pose estimation in video. And we published in Civopia 2023. So we are interested in video-based 2D pose, not 3D at this point, 2D pose estimation, because the 2D is already difficult. And to tackle the human pose estimation in 2D pose estimation so far, most of the works only focus on the frame by frame estimation. Why? Why is this limited to frame by frame? Why can we use the videos? Because the video is difficult to handle, and most of the videos are including many background filters and the motion filters, etc., more noise components. So that's the real question that we have to tackle. How can you get rid of this? So here, the task is from the image sequence. We try to find each individual, the interesting frames, pose. We estimate the 2D poses from each image. So of course, there have been lots of work trying to tackle to try to utilize the temporal information in video for the human pose estimation, especially the moving camera. But as you can see, the most naive way we could think of is using optical flow, right? But optical flow-based method, which is literally the frame-by-frame difference-based information, extraction method, is suffering from the background of the camera moves and also image blurring caused by the visions. Now we try to find a better way to focus on the more interesting better way. So that's what we try to achieve. And then this is our answer to the question. So we use newly designed a new architecture, which is mainly, this part is nothing much because we just utilize the previous existing state-of-the-art human pose estimation frame by frame. For the feature extraction purpose, the key part will be the mutual information component. That's what we newly designed. So more in detail. So each frame here, the key frame is here, and the just before and after frames. This backbone frame is HRNet, which is the state-of-the-art human pose estimation. From each image, we could extract the features in different levels, and then we took the difference in the temporal domain. So we took the temporal differences for each levels, and combining this, now we want to disentangle the information of the interesting point on non-interesting point, which is background for cases. That's we adopted mutual information rules here. And then using out of this, we only focus on the interesting point, which we believe with the human component in there. Then we could estimate the heat map. So this is a very simple and efficient way for differentiate between the background and the motion blurring on like those noise cases. And we could achieve the best performance by then, and on the public data set. And these are the quantitative results we could get. So compared to the other state-of-the-art method, ours is okay. It's better to see by video, I think. Here. So this one is much smoother than the frame-by-frame method because it's like temporal information engaged. And also, it's very fast moving, right? And also, there's fast dynamic motions we could relatively accurately, precisely estimate. Of course, it's not perfect, but it's much better than previous method. That was the mutual information based action, this spatial temporal action pose estimation. Now, right after that, maybe then in computer vision domain, diffusion model is very, very popular. So everything now becomes a diffusion, like a GAN-based method now already replaced with diffusion model, and generation is very, very big topic now. So we try to maybe we can combine generation approaches into the human pose estimation. That's our first attempt because it's fancy. And then we made this one very quickly, actually. So we call that as diff-pose because diffusion-based pose estimation method, which was published last year ICCV in Paris. It's also collaboration with Jilin University. So this is the very first formulation of the human pose human 2D video pose estimation, human pose estimation with the diffusion framework, which we formulate like previous methods so far, which is finding the key point positions from each image frames accurately. That was the main purpose. Maybe we can formulate it in a different way, which is maybe we can generate the human heat map, key point heat map images given each image features. So we formulate in a totally different way. I think this is a very clever way, and this is the very first approach and the first successful result. So by the way, the diffusion model is for those who's not familiar with that. So diffusion model is starting from the noisy input, which is totally random, and then through the iterations, like denoising processes goes through and through, it can generate something we want at the end. right? And the network itself is learning this diffusion, denoising process, right? So here, the input, in this case, the inputs are this random, the image and the random, Gaussian random noises. And then as the processes, so some denoising processes goes on. Now, at the end, we expect the network to produce a heat map point, each key point, each body point in a heat map, right? And we made it. So actually, the algorithm itself is relatively simple. There's nothing much new. So we just adopted, we formulated the human process estimation for the diffusion model formulations. And there are not many new stuff. So we started from BIT, which is transformer-based method, which use the backbone network and the extracted features, and then we trained the post decoders that way. So this is the very first attempt to apply the diffusion model, and it's a new way of formulation of the human process estimation work. And to be honest, I mean, look, I'm sure the videos, the performance are similar than the previous, not much different. It's only 6 months difference, the research, right? And the numbers are similar, actually, to the benchmark. But we believe this is a new approaches we opened up for this post estimation research. So we value that high. And then, okay, then we continue this. Okay, now we can generate the human pose, given the input, given the images, right? Now probably we can generate something different, something more interesting, something in 3D, more personalized. So we continue the work, and this is a collaboration with the Seoul University. And so this is very new work, hasn't been published yet, so it's going to be published in CIVOPR in June this year. So we call them MOST, which is motion style transformer between diverse action contents. So this one is basically we could generate the key point. Now probably we can generate the 3D pose movement to personalize the purpose, personalize the person or different persons of motions. I think this is very important because now we try to, I'm going to show later about our application of this one to the robots, but we believe the human and the robots are going to work together or going to live together, and we try to provide more personalized assistance. Then it has to somehow generate, or it has to adapt to those personalized, being service persons, right? Postures or motion actions, etc. And we believe this kind of style transfer algorithm can be useful for that. So because I have some problem with the codec here, and then this motion style transfer algorithm is like this from the content video, which is old run, and then we extract the style from another image. So here, from this image, from this video sequence motions, we take the content, which is run. From this image sequence or motion sequence, we take the style. And then we're going to combine this from like the style to the content, and then generate a new one, which is proud run. Let's see. Now it's old run, and then proud punch, and then now we can generate proud run. This has been, tried. Of course, it's not a very brand new work, but the other previous works, they only focus on the same content. They only change the style. Now we are going to change the content as well. This is very challenging task. So in the TOG, transaction graphics, so they try to, we applied the same algorithm, implemented, and apply this case like angry jump and strut kick, then the result is not satisfactory enough. Because the algorithm wasn't considered this kind of style transfer. And the other one as well, it's not perfect, right? So we newly design a new architecture, which is like this. We design on transformer, the Siamese transformer, which is taking the like a content motion information and the style motion information separately, and then we disentangle the information into and then combine to generate the new one. The idea is very simple. But for doing that, we design two new loss terms, which is the content consistency. So the old walk plus old jump should be the same old walk, right? Because the style didn't change. Even after the iterations, the style the content should continue to stay the same, and same to the style consistency. So this is a new idea we introduced. So I'm going to show you some video result. So this is the neutral one. And then we try to combine into the proud jump. And then we take the style, now it's old and strut jump, to the same content, different style we could make. Also, the comparison against the state-of-the-art method, like old kick, proud punch. Now, the state-of-the-art is very weird. We could make it work. Yep, the project page is on and the code is also released. So please feel free to test our new method. Okay, so now I have introduced some briefly about the human pose related works. I'm going to show how the human pose related works, like vision-based approaches, can be applied for the real applications. So this is now quite old, 2020. So, but this one is I think is very interesting work to introduce, because it was initiated and proposed by the undergrad students actually. So he came to me and he said he wanted to help his blind friend enjoying his like indoor climbing together. Sure, maybe we can do something with computer vision tasks, because the blind people also wanting to enjoy the same sports as the non-blind people. But the only way they can do is they need some specialized two people to help the assist, to provide the assist, and also the kind of an auditory help or like guidance needed. Now we have computer vision tasks as algorithms. So we use the depth camera and we calibrate the camera, and then we perform the skeleton tracking of the person climber, and also based on that we could design the route for the specialized person, and also we can monitor whether the route and the person is like making a proper move based on the route we designed or not, and then we could provide auditory feedback. So for example, here this is the starting point and end point. We could estimate each in the hand and the foot position, and this is called moon board, which is standardized indoor climbing board. And there are many different ways to achieve kind of route to get to the goal. And they have to follow the specific, the route and the steps. And this algorithm could provide whether the person actually hold with right hand or left hand. And then we made it automated and provide auditory feedback, which is similar to the parking sensor of the car, like different, we change the frequency, the tonal feedbacks. And it was very successful, and the people actually enjoyed it. We couldn't test on the blind person because of the health and safety issues, but the non-blind people, they also could enjoy the route monitoring. And also we worked on the ICOP robot for the mimicking the human motions and learning by self. And also we worked on the personalized assistant for the dressing. And that was the very first work we tried so the robot has to understand the human's personalized disability and could provide the proper trajectory for the dressing, right? And we continued the work, and this is the last year's new work. We not starting from the human, the health and the human given the clothes. Now the robot has to understand and grasp the gown from clothes from the hangers itself. And then that's what we try to achieve. But still, those will be far from the perfect. Yeah, that's the research way we try to achieve and toward. And that's the human body pose. Any questions so far? No? Okay, good. And the next one is hand. So the second the topic, the hand. So the hand related research, a little bit of history. So I started my postdoc research at Imperial with this topic in 2013. And at that time, there was no deep learning. There was only random forest, and there was no big data sets. Actually, there were only 3 or 4 hand-related papers exist. And I'm proudly say that this is our very first hand-related large-scale data set we generated. And now it is still widely adopted for the hand community. So since then, my research on hand is focusing on the temporal information and the hand model generation and interacting object understanding. These days, I'm very much interested in this hand object one. So I'm going to talk mainly about this. So this hand object interaction, hand object interacting object pose estimation and shape estimation, this is very challenging task, surprisingly. Maybe not surprisingly, because the hand is very small and is moving very fast, especially compared to the human body. And it's very difficult to put the markers on here. And it's very largely self-occluded and occluded by object as well. And it's the interaction happens. So, but good thing is hand and object can be the mutual kind of cue for the pose and shape estimation because they're interacting together. And this is the very first work in 2022 Sibopia. We firstly combine this hand object information together, and we generate a new architecture, new framework, which is collaborative learning framework for the work. So the 3D hand object pose estimation from the single RGB image. It's not the depth image. It's single RGB image, and we assume that we do not have the object prior model. But we have to do this, right? Because human can do. So we try to entangle in the very first stage in a naive way. Maybe we can just include the hand information, object shape information together and mix it, let the deep learning works. That's what they tried. But very soon we realized that it doesn't work because there's no information about the contact and the interaction at all. So I'm not going to talk about this algorithm much, but we designed a new graph neural network and attention mechanism to be able to handle that properly. And this is our result. So these are single RGB static image, and these are the output. Again, we do not started with any 3D object model, But as you can see, the pose of the hands and the shape of the object are relatively accurate in 3D. Another thing, it looks good, but hidden part is very slow, to be honest. It's very like each frame, it takes about 10 minutes for the estimation, right? Very slow, but we didn't specify it in the paper, right? Sorry about that. But here it looks good, but one of the main reasons why we do this to link it, integrate it into the graphics or VR or even human robot understanding, human robot interaction, right? So we put this into the physics and simulator of the generated the human the hand object, but even a very small gap between due to the errors, like 1 millimeter, 2 millimeter gaps can induce this kind of slide, right? Because the contact information was not properly estimated. So in order to make this table graph, or in order to make a proper interaction estimation, now we realize that contact estimation is the key. So we move on to the contact estimation with hand and object. So this is there exists luckily the data sets, contact data sets. These are the examples from the data set. Why contact is important? Because these are the heat map of the hands. Because just touch. But just looking at this heat map, human can surely estimate what was the human hand pose like, right? Like hammers, the mugs, you can estimate how it was felt, how it was stressed. I think it's very important too. And we need to utilize it for the human hand object interaction. So we proposed a new algorithm, which is SQL contact. So this is a new work, and we could propose the new semi-supervised learning framework for the hand object pose estimation and the contact estimation properly. The contact this is another one, but quickly. How can you label this? Human object and hand. Do you have any idea? How can you label it? It's very difficult to collect those data sets, to be honest, right? So the data set scale, deep learning, the more the data set, the more accurate label the data set you have, it's easy task. But for this specific task, it's not easy at all. So luckily, these guys, they cleverly introduced a new idea, which is they printed, I don't remember exactly the number of the object, but they 3D printed object with the CAD model. And then they build a system like a multi-camera system with the IR cameras, infrared. So the human subject grasp it, and then now they took a photo of the latent heat. Yeah. So that's how they could make it. But it is very difficult to scale up, and it's very difficult to duplicate the same system.
I was thinking you can put the color on your finger. No.
There could be one solution.
Yeah. I don't know, but I think this is simpler.
Yeah.
With it is simpler. I agree.
Yeah, and some people consider to build it like graphics manner, but it's also very difficult work to do, make it realistic. So we at the time we conducted this research. There's some problem with the data set, limited, very small scale, limited data set, and that's why we introduced the semi-supervised learning, because now we have very small portion of the labeled data set. Now we want to enlarge it or maximize it. So that's the algorithm, and then eventually we could. So the initial pose, then we could estimate the contact, and based on this, we iteratively refine the poses, and these are our results. Compared to the ground truth, it's relatively much better than the previous. So that was the 2020 work. Now last year we move on. How can you make it? How can you combine the very fancy works like using attention concept and rendering concept and the generation, which is very, very trendy. Sure. the nerve. That's our reason. Because the nerve is one. So nerve means the neural radiance field, which was very popular last year from 2022-ish. And then now, interestingly, now it's no longer be widely used adopted because the Gaussian splitting is introduced last year, end of last year. So most of the work now replacing very quickly the nerve, but nerve was very powerful. But here the basic idea is now we have some data set having multiple camera inputs, interacting the object. Sure. Now we have nerve. Now, which means we can render it 3D, right? Now we can render different views using nerve. Out of this, maybe we can maximize our information for the hand object contact point estimation. That was the great idea. So from the input image, it can be one single camera, but the like rotating videos, or it can be the multiple camera system, doesn't matter. But using the nerve, we could estimate, we could render the 3D views from all different views. And then based on that, we could relatively accurately estimate, okay, from the source video, we could estimate the poses, like initial pose estimation using this state-of-the-art method. And then we could render the free viewpoint rendering. And then out of this, now we could maximize, keep iterating it for the refined poses. Very simple, right? Yeah. I'm not sure whether the computer vision is no longer the mathematics engaged. It's very just fastly adopting, research now. So, because everyone is running so quickly, moving forward. We don't know whether we are heading towards, but everyone forget this. That's my feeling, but now we can do something exciting, right? Because the already very exciting, fun to enjoy the works are released. So that's out of this, this can be applied to multiple view videos like this from the videos to generate the human object interacting multiple view rendering. And then out of that, we could estimate better the the hand object contact point and the pose estimation correctly. Or it can be the one single monocular view rendered in the multiple view, different 3D, then we can estimate. Yeah, that's the new kind of new approaches that we try to tackle. And we are also now we have already moved on to the Gaussian splitting method because the nerve is super slow. That's the problem of nerve. So the training and rendering is very slow in nerve, and Gaussian splitting, thanks to the some clever people working on the CUDA coding itself, Gaussian splitting is much faster and less noisy. Now we have already moved on to adopt the Gaussian splitting cases. And then, okay, another interesting combination we could try was using maybe 3D rendering plus attention. So this is a collaboration work with Google Research. So my student Eldon, he did the internship at the Google in Toronto, I think. Yeah, Toronto. And he joined a Google Glass team, and they said, okay, guys, we are very much. They said they're working on the Google Glass new version, and the new Google Glass has two cameras here, which is egocentric view, and two cameras. So they want to do the human hand, natural human hand movement and pose estimation from the multi-camera, which is 2, and from the egocentric view of the 2 hands. That's the only limitation. So yeah, sure, why not? We can do it. So this is the motivation for their own research, and then we started looking for some data set. But interestingly, there are lots of very different kind of data set exist, but not many for the two hands. So we started generating a new data set. But the hand data annotation is very tedious job and difficult to do. So we started from the synthetic simulator hand graphics-based synthetic images for two hands for the high fidelity images. And it should be the egocentric view because it's actually the blue glasses purpose. And then we included, we also collected real hand cases. Also, we also added some synthetic views to make it more realistic. So this is the idea. So from the two images, because two cameras input two images, then we use the soft attention fusion because some people might ask, because it's a two camera system. If the camera is already calibrated, why do just use the multiple view fusion? Because for the glasses it's bending, right? The calibration doesn't work. So we had to find a way that we fuse the two images in an algorithmic way. So that's why we think about the attention-based method. And then we adopted the transformer encoder, which is from the hand mesh model. We try to reconstruct the graphics, this hand mesh model parameters properly. And also, for the graphics, this is a big problem. The collision is largely happening because each mesh model, those are the node, and we cannot avoid. It's very difficult to avoid making collision. So we introduced a new node stuff. Then, compared to the other method, which is ours, much cleaner. And also it works quite well because thanks to the large scale data set we generated, we could handle self-occlusion and various lighting conditions and very diverse background cases well. And the occlusion, this like intrusion of the nodes, we could make it like kind of as a post-processing, we could fix it somehow, but not perfectly, because, for example, in these cases, we try to avoid the one finger's collision, then now it's stuck to the other fingers. This kind of is still very challenging. Okay, but it quite works well, and like quantitatively, it works quite efficient way as well. So that's the thing. What can you do with this hand? Because you guys have already probably watched the Apple Vision Pro. So that's another kind of, it's a present, it's not future anymore. So the VR, AR, the hand tracking, natural, bare hand tracking should be kind of by default, should be done. We don't know yet how the Apple Vision Pro made it working. I haven't tried the hand properly yet, but that's the current where we are, and that's the ordinary people expected, right? So from the camera, so they want to find a way, the algorithm work without any more the conversion, the devices for the interaction. So it should be a hand, bare hand, two hands, and even with the object, right? So that's the thing, and I think this will be a very near future that we should focus on. A little bit of promotion is that I have been organizing the hands workshop in ICCB last year, and we are going to organize again in ECCB this year. So if you're interested in hand, then please stay tuned for this workshop series, because you will see we try to select curate the most advanced research groups in hand, so that you can see what's going on in academia. And we try to also discuss further about industry directions. Of course, the Apple is not attending, but we can imagine what's going to happen soon. So that's about the hand. Any question? No? Okay.
So are you saying that on the Apple version, they've solved this issue of collision?
To be honest, Apple Vision Pro is very, they're working very secretly, so we don't know how they
But
make
it
it work.
appears to be the case. It's not that.
Yeah, somehow they could, I mean, hands tracking, I'm not sure whether you have tried the Microsoft HoloLens too. So it's already very accurate. So if you are using that camera, sure, it's already a very easy task. But with the single RGB camera, I'm not sure. But they somehow they managed to work. But I think they use at least multiple camera system. It is very much, the Apple Vision Pro is very limited view and limited action, right? It's not interacting more like holding stuff, right? So it's relatively restricting its own utilization, right? Specific purpose. Now I'm going to introduce about the eye gaze, which is the last topic, right? So the gaze estimation is a very important task to understand the human correctly, because the human are talking a lot through the gaze, through the face, and this their movement. So there are in gaze estimation research, it can be largely categorized into three topics, which is 3D gaze estimation, and gaze following, and point of regard estimation. So 3D, especially in my group, we are mainly focusing on these two, because this one, point of regard, is already the commercial product for like Apple, Samsung. They are doing very well. For example, if you want to unlock your phone, iPhone, then you have to look at it, right? Which means they already understand roughly where you're looking at. So in my group, we are focusing on this research. So the gaze estimation is even harder than the human hand research, because we cannot put the markers there. That's right. And eye is very small. It is even smaller than the hand, and it's moving very fast. I'm not talking about I'm talking about the smooth person only, right? But it is very fast already. Keep moving, and also the occlusion, frequent occlusion by the eyelid and blinking, and also head pose are more extreme cases. It's kind of that, and also different domains like makeup and different illuminations and eyeglasses, etc., etc. It is even more challenging. I mean, the eye gaze research has very old history, but still is very, very difficult task. I didn't put it here, but another important thing that we have to, I didn't put it here, I didn't mention clearly, but another big challenge is that anatomically, the human eyes, I mean, we have pupils and also retinas, and we believe that the eye, the optical centers, I mean, what we see is exactly aligned to the optical center lines, right? Which is not true. It is biased, slightly tilted, and because our retina is not, I mean, retina is slightly different, right? And each person has different eyeball size, and that angle everyone is a little bit different, which means the personalization is very, very important too for them. And due to these issues, like if you use the expensive high cost eye tracker from Kobe's, which is about 20,000 pounds, then probably you can make your error rate between the 1 degree ish. But if you just use the vision based approaches, then the minimum we could try so far, the error is about 4 to 5 degree. 4 to 5 degree, it doesn't look good, it doesn't look big, but imagine it's the angle between the branches and actually the point you're looking at. So the further the object is, then the angle becomes very large. So the gaze, as mentioned, has many challenges that could make it accurate. So the main, but I think the biggest issue at the moment in this community is the data set collection issue. So we designed a new method, a new algorithm framework for the data collection using the motion capture system and generative models. So we proposed and released a new data set, which is called RTGene, and which works quite well with just Kinect camera and just ordinary webcams, and we even could control the wheelchair with eye gaze with this laptop camera. It works quite well, and this roads package is available, and we have been keep updating the roads packages. So now, if you're interested in using the visual-based gaze, then this can be the good solution. So try. And now this is the current state of the art in the result you can expect from this roads package. If you use GPU, then it runs in real time. Please feel free to try. And it's the very highest the performance issues. Then now we focus on how we can improve that by algorithm last year. So we tried to combine this attention 3D rendering generation keyword together. So this work was published in Civil.pl last year. It's collaboration with ETH Zurich and NVIDIA and TUDO together. It's called Gaze Nerve. So we the gaze. So we try to tackle two problems, which is data set gaze realistic, large scale, personalized gaze data collection is difficult, right? So we try to synthesize it. How we control that, how we gather the personalized 3D views, we are going to use Nerve. That's the baseline. Then we started from the previous famous work with the head nerve. So it's a nerve, basically a nerve, but they embedded some code here. So they could control the rendered images, like different face expressions, or like movement of the albedo illumination identity. Then now we modified it a little bit, so make it more focused on the eyes, so we can control the eye movement similarly. So these are the results we could get. Okay, here. So the good thing is the gaze nerve out of this. Now from these images, we could render all arbitrary views, 3D views of the specific person, and then we could also generate the arbitrary eye gaze movement, right? But some limitation is that there's still some noises in the face, rendered faces, right? Low quality. Now, because that's due to we didn't focus on the 3D high fidelity of the face images. Now we move on to make it more high fidelities. So we try to make it like multiple view images. We want to render it by fitting the 3D human model, face model, like this way. For multiple views, we utilize already existing face model. We fit it, okay? So fit the 3D model, and then we could generate multiple views of the view. And then we render this rendered image and the original image. This is one lost term. And then also we focus on the face landmark shouldn't change, right? And then people locate position. Then based on that, we could render the eye aware in the radius field. I'm going to show you better results then. So we only rely on the 9 frames.
this is the result. So here it's a little bit creepy. But compared to the previous gaze nerve, so the out face are much more high fidelity and eyes as well. Now we could control the faces in this way. This is a kind of, now the widely adopted way that we can generate enlarge the data set using the algorithms. So this is the 3D gaze estimation result. It's quite reliable, right? So now I'm doing one research grant with Korean partners. So they want to estimate the eye movement, or I mean, they want to research. We are doing the research on the online education system, and they want to keep monitoring the students in the gaze directions over the training. Okay, this is new, and then not only this, and not only this, but now these limited cases, but we want to make it more applicable for the various cases. Now we are interested in the in-vehicle situation. So this is very new work published in Sibopia, and this is the so it's about the new framework, new algorithms, and the new approaches generating data set for the vehicle situations. So by the EU regulation, for the autonomous, not only for the autonomous, all the vehicles has to keep the human monitoring system to provide for the safety issues, and then so all the cars now now currently have their own eye gaze monitoring system. Now eye gaze is like kind of eye relate the face or eye awareness recognition system there. And this is our result we generated. So here, the data set so far in eye gaze research is very much limited. So most of the data sets are outdoor or indoor cases. The vehicle related one is very limited so far. And also look at the number of subjects this method has many, but none of them has the gaze label because it's difficult to label. They only focus on the zone. So whether it's looking right, left, but we newly introduced a new way of doing that. And also the data set itself has many different, it has more diversity. So it has some illuminations, glasses, genders, wearing the masks, all different cases. So this is the vehicle setting. So we put the camera front, and also okay, here. So we put the markers in the windshield window, and also perform the calibration, and then we could get the camera and calibrate it, and then we could get the multiple views as well. So we generated the transformer-based architectures. Basically, we could get the best performance for the gaze. Let me just skip this. But basically, we have moved on to the autonomous vehicle related eye gaze, and we are very much focused on the driver monitoring system now. So there are many applications for the eye gaze, not only for the drivers, but also the games or different UIs or the common advertise effect monitoring, etc. This is one example of my student monitoring the students' awareness over the class. So we constructed the 3D view of the small lecture room, and then we track the student's face direction and the gaze direction and project it. Now we could estimate measure the attention level of the students out of that. So we are managing we keep curating the eye gaze papers. So if you are interested in the eye gaze research, please search for it, and then.
Oh, okay.
Okay, it's almost finishing, sir.
Almost finished.
Yeah.
Sorry, thank you.
And then we are also organizing GAZE workshops. So if you're interested in that, then please stay tuned. And now, okay, now it's conclusion. So we are very much, we have focusing on various in the combination of the keywords. Now it's the era of generation and LLM and multimodal. So this is what our next directions. So LLM plus multimodal. So LLM will be the key, large language model will be the key of it. And briefly, we submitted hand pose estimation with LLM. And also the gaze estimation, gaze image generation with large language model. That's the direction. I think that's the very near future, right? And this human-centered visual learning can be applicable many interesting applications, right? Yeah, I think that's it. That's sorry for the rush at the end, and that's my talk. Thank you very much.
Yeah, and I think because they booked the room at 3, so if you have any questions, we can discuss outside of the room.
Sure.
I think it's better. So if you have any questions with the speaker, just try to catch him because when are you leaving?
I don't know.